Welcome back, everyone. Today we're going deep, really deep, into the world of ceramics.
Ooh, ceramics. That sounds pretty fragile.
You know, it's funny you say that because we're going to talk about why ceramics have that reputation for being, well, a bit delicate.
I'm all ears.
But first, we need to lay the groundwork. We're cracking open a chapter from a material science textbook, and let me tell you, there's more to these materials than meets the eye.
I can imagine. We encounter ceramics every day, from our coffee mugs to the tiles on our floors.
Exactly. And even though they seem simple, at the atomic level, they're incredibly complex and fascinating.
That's what makes this deep dive so exciting. We're going to unravel those complexities, starting with the most basic question. What exactly defines a ceramic?
Right, because I have a feeling we're not just talking about pottery here.
You're absolutely right. It's a much broader category than you might think. Ceramics are inorganic, non-metallic materials, and they're often formed by combining metallic and non-metallic elements.
Okay, so we're talking about compounds, not just single elements.
Exactly, and that's one of the key differences between ceramics and, say, metals. Metals are typically made of a single element, like iron or copper, whereas ceramics have at least two elements.
So it's like combining different ingredients to create a unique dish. The elements determine the final product.
A perfect analogy. And the way these elements mix at the atomic level is through ionic bonding.
Ah, ionic bonding. That brings back memories from high school chemistry. Refresh my memory. What's going on with those electrons?
Basically, in ionic bonding, atoms exchange electrons to become charged ions. The atom that loses electrons becomes positively charged, and we call that a cation. The atom that gains electrons becomes negatively charged, and that's called an anion.
And of course, opposites attract, so those cations and anions are drawn to each other.
Right, precisely. And that attraction leads to the formation of a stable three-dimensional structure. It's like a delicate dance of charges.
It's incredible to think about how those tiny charges create the materials we see and touch every day.
It is. And the way those ions arrange themselves is crucial. It determines the type of crystal structure the ceramic forms.
Crystal structure. So we're talking about a very ordered, repeating pattern of atoms, right?
Exactly. And these crystal structures are incredibly important because they dictate the material's properties. It's like the foundation of a building.
Okay, I'm starting to see the connection between structure and properties. Give me an example of how these crystal structures play out in a real-world ceramic.
Well, take table salt. It has a simple cubic structure with each sodium ion surrounded by 6 chloride ions, and vice versa.
Wait, so regular table salt is a ceramic. Mind blown, I never would have guessed.
It is. And that simple repeating pattern gives it its characteristic properties. There are many other types of crystal structures too, like cesium chloride, zinc blende, fluorite, and perovskite.
So there's a whole family of ceramic structures out there, each with its own unique arrangement of ions.
Exactly. And those arrangements determine whether the ceramic ends up being hard or soft, transparent or opaque, conductive or insulating. The possibilities are endless.
It's like each crystal structure gives the ceramic its own personality.
That's a great way to put it. Now, speaking of different types of ceramics, in the intro you mentioned silicates. Where do they fit into this ceramic family tree?
Right. Silicates. I know they're a huge part of the Earth's crust, but I'm not exactly sure what they are.
Silicates are essentially materials made primarily of silicon and oxygen, the two most abundant elements in the Earth's crust. Think rocks, sand, clay, they're all based on silicates.
So we're talking about the building blocks of a lot of what we see around us.
Absolutely. And the key to understanding silicates is this building block called the silicon-oxygen tetrahedron.
Tetra. Something. Break that down for me.
A tetrahedron is basically a pyramid with 4 faces. In the silicon-oxygen tetrahedron, you have a silicon atom at the center and 4 oxygen atoms at the corners.
Okay, I'm picturing it. Now, how do those tiny pyramids build up into something like, well, a giant rock?
That's where things get really interesting. These tetrahedra can link together in different ways, sharing oxygen atoms to form chains, sheets, or even intricate 3-dimensional networks.
So it's like they're holding hands to build all these different formations.
Exactly. And this incredible variety of structures is what gives us the different types of silicates we see in nature.
So, like, what kind of variety are we talking about here?
Well, you have crystalline silica, like quartz, with its very ordered structure, which gives it its hardness and clarity. Then there's silica glass, with a more random arrangement, making it transparent and brittle. And we can't forget layered silicates like clay, which are essential for pottery because of their ability to be molded and shaped.
Wow. So from the sparkle of quartz to the moldability of clay, it all comes down to how those silicon-oxygen tetrahedra are arranged.
It's pretty amazing, isn't it? And speaking of amazing structures, there's one element that often gets grouped with ceramics because of its diamond form: carbon. Yeah.
Diamonds. Now we're talking. But carbon isn't just about sparkle, right?
Absolutely not. Carbon is incredibly versatile, and it can take on many different forms, all thanks to variations in how the carbon atoms are bonded together.
Okay, so walk me through some of these carbon forms. We've got diamond, which is the hardest known material, right?
You got it. Diamond's hardness comes from its super strong covalent bonds, where carbon atoms share electrons very tightly. But then you have graphite, which is so soft and slippery that it's used as a lubricant.
It's amazing how the same element can be both incredibly hard and incredibly slippery. What makes graphite so different?
The difference lies in how the carbon atoms are arranged. In graphite, they form layers, and the bonds between those layers are much weaker than the bonds within the layers.
So those weak bonds between the layers allow them to slide past each other easily, making graphite slippery.
Exactly. And there's more. We also have these fascinating structures called fullerenes and carbon nanotubes.
Okay, those sound pretty high-tech. What are they all about?
Fullerenes are these incredible soccer ball-shaped molecules made of 60 carbon atoms. They have intriguing electrical properties that could revolutionize electronics.
So fullerenes are like tiny molecular soccer balls with the potential to change the world of electronics.
You could say that. And then we have carbon nanotubes, which are basically rolled up sheets of graphite. Imagine a single layer of graphite, like what you'd find in a pencil, rolled into a tiny tube.
I'm picturing it. What makes those nanotubes so special?
They're incredibly strong and stiff, with potential applications in everything from aerospace components to advanced electronics. Imagine lighter, stronger aircraft or flexible screens that are practically indestructible.
Wow, so carbon is kind of the future is now element of the materials world.
I'd say so, but let's not forget that even these amazing materials have imperfections.
You're talking about those tiny cracks and imperfections. Aren't those the things that make ceramics, well, prone to shattering?
They can be, but it's more nuanced than that. We need to look at the types of defects that occur in ceramics and how they affect the material's behavior.
All right, let's dive into those defects. I have a feeling things are about to get interesting at the atomic level.
You're absolutely right. Buckle up. So those defects, those little imperfections in the ceramic structure, we have vacancies, which are basically empty spaces where an atom should be. It's like a missing piece in a puzzle.
Ah, okay, vacancies. So something's just not there. Makes sense. What else?
And then we have interstitials, which are kind of the opposite. It's where an extra atom is squeezed into a space where it doesn't really belong.
So it's like trying to cram too many clothes into a suitcase.
A great analogy. Now, the thing to remember with ceramics is that we're dealing with ions, which have positive or negative charges.
Right, those cations and anions we talked about earlier. So these defects must affect the overall charge of the material, right?
Exactly. Any defects have to maintain electrical neutrality. The total positive charge has to balance out the total negative charge.
So it's a delicate balance. It's not just about atoms randomly hopping around. It's about keeping those charges in check.
Precisely. And to keep things balanced, defects often occur in pairs. For example, we have the Frankel defect. This is where a cation, a positively charged ion, jumps out of its normal spot and into an interstitial space.
So it's like that cation just can't sit still.
You could say that, but because it's the same ion moving, the overall charge remains neutral. We also have something called the Schottky defect, where a pair of ions, one cation and one anion, are missing, leaving behind two vacant sites.
So it's like a double vacancy, but because one's positive and one's negative, it's still balanced.
Exactly. Now, another thing that can disrupt this delicate balance is the presence of impurities. These are basically atoms of a different element that have snuck into the ceramic structure.
Like little imposters trying to blend in.
Yeah.
Do they always cause trouble?
They can certainly shake things up. Impurities can be substitutional, meaning they replace one of the original ions, or interstitial, meaning they squeeze into those tiny spaces.
So depending on their size and charge, they can either fit in or cause a bit of a stir.
You got it. And to maintain that electrical neutrality, the ceramic might create more vacancies or interstitials to compensate for the impurities charge.
It's like a constant game of adjustments to keep those charges in check. Okay, I think I'm starting to get a handle on these defects, but how do they actually affect the properties of the ceramic? Do they make it weaker, stronger, or something else entirely?
That's a fantastic question, and it gets to the heart of why understanding defects is so crucial. But before we jump into that, I think it's time we look at how atoms move around within these ceramic structures. Have you ever heard of diffusion?
Diffusion, yeah. I remember that from a deep dive on metals. It's basically how atoms move around within a material, right? Like a slow atomic dance.
Exactly. But I have a feeling diffusion in ceramics might be a bit more complex than in metals, what with those charges flying around.
You're probably right. It's not just about atoms randomly hopping around, is it?
Not at all. In ceramics, we have both positive and negative ions moving around, and that charge neutrality always has to be maintained.
So it's like a carefully choreographed dance, where every step has to keep things balanced. I'm intrigued. Tell me more.
Well, to understand the steps of that dance, we need to talk about phase diagrams. Now, I know those can seem intimidating at first, but they're really just visual guides to understanding how a material's phases change with temperature and composition.
Phase diagrams.
Right.
So we're talking about those maps of thermodynamic possibilities, those charts that tell us what state a material will be in at a given temperature and composition.
Precisely. And they're especially important for predicting how ceramics behave at those high temperatures they often encounter during processing and manufacturing.
Right, because ceramics aren't exactly known for being room temperature creations. Think kilns and furnaces and all that.
Exactly. So let's break down one of these diagrams. Let's start with a simple one, the aluminum oxide chromium oxide system.
Okay, so I'm looking at this diagram, and I see temperature on one axis and composition on the other. What else am I looking at?
Well, the diagram is divided into regions, kind of like a map, representing different phases. You'll see regions for solid, liquid, and even a mix of the two.
So by knowing the temperature and the composition, I can use this map to pinpoint exactly what state the ceramic will be in. Pretty neat.
It is. Now let's look at a slightly more complex system.
Mm-hmm.
Magnesium oxide, aluminum oxide. This one's interesting because it has an intermediate compound called spanyl.
Spanyl. Okay, so we're not just talking about a straightforward blend of the two oxides anymore. Something new has emerged.
Exactly. Spanyl is a distinct compound, but what's fascinating is that it can exist over a range of compositions. We call this non-stoichiometry.
Non-stoichiometry. So the ratio of magnesium to aluminum ions can deviate from what we'd expect based on the ideal chemical formula.
Precisely. And this flexibility can affect its properties, like its color, electrical conductivity, or even its melting point.
So even slight variations can have a big impact. It's like fine-tuning a recipe to get the perfect flavor.
A great analogy. Now, speaking of non-stoichiometry, there's another system I want to mention. The zirconium oxide calcium oxide system, or zirconia calcia for short.
Zirconia calcia, that one sounds familiar. Doesn't it have something to do with stabilizing zirconia?
You're right. Pure zirconia has a bit of a structural issue. At high temperatures, it undergoes a phase transformation that causes a significant volume change. And that can lead to cracking, which isn't ideal for making durable ceramics.
So it's like zirconia has a meltdown when things get too hot.
In a way, yes, but by adding a bit of calcium oxide, we can prevent this drastic transformation and make zirconia much more stable at high temperatures.
So the calcium oxide is like a stabilizing force, keeping zirconia in check. Kind of like a chaperone at a high school dance, making sure things don't get too wild.
I like that. Now, one last phase diagram I want to touch on is the silica-alumina system. This one's crucial because silica and alumina are the main ingredients in many ceramic refractories.
Refractories, those are the materials that can withstand extreme temperatures, right? Like what you'd find lining a furnace.
That's right. And the phase diagram helps us understand how silica and alumina interact at those high temperatures so we can predict their behavior and design better refractories for different applications.
It's like having a cheat sheet for understanding how these materials will behave under pressure, literally. Okay, so we've explored these phase diagrams. What's the main takeaway here? Why should we care about these charts and graphs?
Phase diagrams are powerful tools. They give us a way to predict how a ceramic's structure and properties will change with temperature and composition. This knowledge is essential for designing better processing methods, choosing the right materials for specific applications, and even engineering new ceramics with tailored properties.
So they're like a roadmap for navigating the world of ceramics.
Precisely.
Phase diagrams, who knew they could be so fascinating?
Right. They're like a secret decoder ring for understanding ceramics.
Exactly. But, we've talked a lot about the unique structures and compositions of ceramics, and even how those pesky defects can influence their properties. But now it's time to address the elephant in the room, their brittleness.
Ah, yes, the brittleness. Ceramics have a reputation for being a bit delicate, shall we say.
That's putting it mildly. We all know that shattering sound all too well. What makes them so susceptible to cracking and breaking?
It all comes down to how these materials respond to stress. Unlike metals, which can deform plastically, ceramics have limited ability to bend and give. When a crack starts to form, it can quickly grow and lead to catastrophic failure.
So it's like an all-or-nothing situation. They either flex a little or completely shatter.
Pretty much. And a big part of this brittle behavior is due to those tiny flaws or cracks that we call microcracks. These act as stress concentrators, meaning they amplify the applied stress at their tips.
So even a microscopic crack can be a weak point.
Unfortunately, yes. And these microcracks are almost unavoidable during the manufacturing process. They can significantly weaken a ceramic material, even if it has a strong overall structure.
So it's like they're almost predestined to have these weak spots.
In a way, yes, but that doesn't mean we can't improve their strength. Scientists and engineers are always working on new techniques to minimize those microcracks and make tougher ceramics.
Well, that's good to know. But even with those advancements, we still need a way to measure the strength of these potentially brittle materials. I'm guessing a standard tensile test where we just pull on the material until it breaks wouldn't be the best approach here.
You're right, a tensile test wouldn't give us much useful information with ceramics. Instead, we use something called a flexural strength test, or bend test.
Okay, so we're bending instead of pulling. How does that work?
In a flexural strength test, we take a bar-shaped ceramic specimen and support it at 2 points. Then we apply a load to the center of the bar, causing it to bend.
So we're basically trying to see how much bending force the ceramic can withstand before it gives way.
Exactly. We measure the stress at which the ceramic fractures, and this is called the flexural strength, or modulus of rupture. It's a key parameter for designing ceramic components that will be subjected to bending forces.
Makes sense. It's all about understanding how these materials will perform under real-world stress. But I'm still curious. Do ceramics ever deform plastically at all, or do they just go straight from elastic deformation to fracture?
That's a great question, and the answer isn't so straightforward. While plastic deformation is very limited in ceramics, it can occur under specific conditions. It depends on whether we're talking about crystalline ceramics, which have that regular repeating atomic structure, or non-crystalline ceramics like glass.
Okay, so let's start with those crystalline ceramics. How does plastic deformation happen in them?
Well, in crystalline ceramics, plastic deformation can occur by the movement of dislocation.
Dislocations, those are line defects in the crystal structure, right? I remember we talked about them in our episode on metals. They seem to move pretty freely in metals. Why is it different in ceramics?
You're right. Dislocations can move much more easily in metals. In ceramics, things are a bit trickier, especially in those with ionic bonding.
Ah, those charges again.
Exactly. Remember, in ionic ceramics, we have those positively and negatively charged ions arranged in a very specific pattern. Trying to move a dislocation through this structure could force ions of the same charge too close together.
And that would create a lot of repulsion, right? Like trying to push two magnets with the same poles together.
Exactly. That repulsion makes it incredibly difficult for dislocations to move in ionic ceramics. Now, in covalent ceramics, like silicon carbide, the story's a bit different. The covalent bonds are very strong and directional, which also restricts dislocation movement.
So whether it's ionic or covalent bonding, those dislocations have a tough time moving around in ceramics. Is that why they're so much more brittle than metals?
It's one of the main reasons, yes. But what about non-crystalline ceramics, like glass? They don't have that regular crystal structure, so how do they deform plastically?
Good point. It's hard to imagine dislocations in something that's basically a jumbled mess of atoms.
You're right. There are no dislocations in non-crystalline ceramics. Instead, they deform through a process called viscous flow.
Viscous flow, isn't that how liquids behave? Like pouring honey or syrup?
It is. In viscous flow, the atoms or ions can slide past each other in a continuous fluid-like motion. It's like a very thick syrup slowly flowing under its own weight.
Okay, I'm starting to see the distinction here. In crystalline ceramics, we have limited plastic deformation because of those stubborn dislocations. And in non-crystalline ceramics, it's all about that slow, syrupy, viscous flow.
You got it. Now, before we wrap up our deep dive into ceramics, there's one more factor that can drastically affect their strength. Porosity.
Porosity. Those are the tiny holes or voids that can exist within a ceramic material, right?
Exactly. And even a small amount of porosity can significantly weaken a ceramic. Those pores basically act as tiny built-in cracks.
Well, that makes sense. If you already have weak points in the material, it's going to be more susceptible to breaking.
Precisely. That's why minimizing porosity is a major focus during the processing and manufacturing of ceramics. It's all about creating a dense, uniform structure to maximize their strength and durability.
So we've covered brittle fracture, flexural strength, those finicky dislocations, viscous flow, and those sneaky pores. What's the final verdict on the mechanical properties of ceramics? Are they inherently weak, or can they be toughened up?
That's the million-dollar question. We've only scratched the surface of this fascinating field of ceramic mechanics. But before we wrap up, I do want to emphasize that while we've talked a lot about their limitations, ceramics also possess some remarkable properties.
That's true. They're hard, they can handle intense temperatures, they're chemically resistant, the list goes on.
Exactly. And scientists and engineers are always pushing the boundaries of what's possible with ceramics. They're developing new processing techniques, creating new compositions, and discovering new applications all the time.
So it sounds like the future of ceramics is still being written. Who knows what amazing breakthroughs are just around the corner?
Absolutely. But for now, I think we've covered a good overview of the fundamental structures and properties of ceramics. We've looked at their diverse crystal structures, their bonding behavior, their tendency to form defects, and how they respond to stress and temperature.
It's been an incredible journey into a world we often take for granted. I feel like I have a whole new appreciation for those everyday ceramic objects.
And there's so much more to learn. I'll leave you with this thought. The next time you pick up a ceramic object, take a moment to consider that intricate world of atoms and bonds at play. It might just change how you view these seemingly simple materials.
I know I will. Thanks for joining us on this ceramic adventure. Until next time, keep diving deep.